This is Concept 2 notes on the periodic table. So now that we have introduced the atom and its structure, it only makes sense for us to then move on and talk more about the periodic table. And so I know you are already most likely familiar with the periodic table, and there's some things that you know about it, but we're going to go into much more detail in this class than you probably ever have before. So after this unit especially, but even the next one too, you will be able to look at this periodic table and know, what are all these numbers for? What are all these symbols for? What do each of these things mean? Not just are they labeled, but what do they mean and what do they tell me about these elements and the atoms of these elements and how that they're going to behave? Because moving forward in this class, we're going to really be talking about what the atoms of these different elements do when they form compounds. That's the core of what we're doing here in chemistry. And so understanding the periodic table is critical. So instead of boring you with a ton of notes on this, we are going to do some discovery stations about this in class where you're going to kind of learn about the periodic table for yourself. And I'll just kind of hit the highlights here. Okay, so for the sake of the video, let's keep pushing. The periodic table. You can tell the following things about an element from the periodic table. All periodic tables should have these few things on there. So first, they're going to have the atomic number for an element. They're going to have the element's symbol, its name, and its atomic mass. Now, some periodic tables will have additional information on there. They will have more to them than this, but they will all at a bare minimum have these. Now, one thing we cannot tell from the periodic table is the mass number of an atom. Specifically of an atom, we don't know the mass number. So let's clarify what the mass number is. So the mass number, not on the periodic table, it is the number of protons and neutrons in the nucleus of an atom. So if you remember, protons and neutrons are 2,000 times more massive than electrons. So we say that the mass of the atom is located in its nucleus. So when we're referring to the mass number, we're talking about the nucleus. What's in the nucleus? The protons and neutrons. Now remember, this number here is helpful. It is the atomic mass. It's related to mass, but this is representing all of the different versions of the element, all the different atoms you have out there of it, and it's kind of an average number. We'll talk more about this a little bit later. For a mass number, we want to know specifically about one specific atom. So just the protons plus the neutrons. So mass number equals the atomic number, which is the number of protons, plus the number of neutrons. So a lot of people refer to that as the Mann equation, but that to me is a little trickier because then you have to remember that protons are the atomic number. So I just remember mass number is protons plus neutrons. That's it. You don't need to get into a fancy equation or anything for it. Just remember that definition. And so let's see if we can figure out the mass number for the atoms that are pictured here. So looking at this drawing of carbon, we don't worry about the electrons. We just look at the nucleus because that's where the mass is. And we see 6 protons and 6 neutrons. So 6 plus 6 gives us a mass number of 12. Here for fluorine, we do 9 and 10. That gives us 19. And then for calcium, we get 20 plus 20, which is 40. So that would be the mass number for this atom. And we are going to pause and practice this because it's really important that you can do these simple calculations of addition and subtraction, that you can use the periodic table and given some numbers, figure out the atomic number, figure out the number of protons, figure out the number of neutrons, the mass number, the number of electrons, etc. So we're going to stop and practice that in class. But again, we're going to kind of keep pushing through with these notes for the sake of the video. So let's talk about isotopes. Not all atoms of an element are identical. So not all hydrogen atoms are the same. Not all carbon atoms are the same. And isotopes are what makes them different. Isotopes are atoms of the same element. So they're going to have the same number of protons, the same atomic number, because remember, that's what determines the identity of an atom. So that's going to be the same. But the number of neutrons in the isotope is going to be different. And if you remember from concept 1, I said the number of neutrons really informs us on the mass of an atom. So if the number of neutrons is different, that means the mass number is going to be different. So isotopes have the same atomic number, the same number of protons because they're the same element, but they have different mass numbers because they have different numbers of neutrons. So let's look at this example. There's hydrogen 1 and hydrogen 2. So hydrogen 1 is pictured here and hydrogen 2 is pictured here. Now let's look at these. Notice that both of them have one blue proton. So they have the same atomic number, which is 1. You can look at the periodic table right now and see that hydrogen has an atomic number of 1. If it has an atomic number 1, if it has 1 proton, it is hydrogen, period. But what you will see is different is this atom of hydrogen has no neutrons. There's no neutrons pictured here, only 1 proton. Whereas this one has a proton and a neutron. It has 1 neutron. And so we say it's hydrogen 2 because that's its mass number. 1 plus 1. 1 proton plus 1 neutron gives me 2. Hydrogen 2. Whereas this one just has hydrogen 1 because it's 1 plus 0. And typically what we see is that the more stable isotope will be the one where the protons and neutron number are the same. And typically we see that atoms of different elements, they have the same as or more neutrons than they do protons, with the exception of one of hydrogen's isotopes and then also one of helium's isotopes. And then after element 20, most atoms have way more neutrons than they have protons. So that kind of changes. But within the first 20 elements, we really see that, if they're having the same number of protons and neutrons, that's what's going to be the most stable. Okay, now, so I kind of already introduced isotope notation here, and you might have been like, what is she even doing? We haven't learned anything about with these dashes. So let's talk about it now. There's kind of 2 different ways that we can notate an isotope. And remember, we have to do this. We have to have notation for isotopes because we cannot tell the mass number from the periodic table. So there has to be a way for someone to tell you the mass number in some sort of notation since you can't just look it up. Okay, and so we have hyphen form and we have nuclear form to do that. Hyphen form is just the name of the element with a hyphen and then the mass number. That's it. So like potassium dash 40. This would be an atom of potassium that has a mass number of 40. If you look up potassium right now on your periodic table, you will see that potassium has 19 protons because it has an atomic number of 19. And if we take 40 minus 19, that will tell us the number of neutrons, which would be 21. Because again, 40 minus 19 equals 21. Okay, now, another way we could write this, though, is nuclear form. And nuclear form is going to be the mass number in a superscript over here, plus the symbol next to it. Okay, so instead of potassium 40, like it's written up here, we would have 40 and then K for the symbol. Now, something to make note of. Nuclear notation can also include the atomic number below the mass number. So like right here below the 40, okay? But this isn't always essential since the identity of the element allows you to determine the atomic number. So I don't necessarily need to put a 19 right here because I know that potassium has an atomic number of 19. So it's almost like redundant in this situation because I know if I know potassium, I know atomic number 19. If I know atomic number 19, I know potassium. But here's a notation just so you can see it, and it would look like this. And the reason why I even show this to you and that it's important is because when we get into concept 3 especially, which is nuclear chemistry, we're going to be doing some kind of tricky things there with some nuclear equations, and it's going to be really, really helpful for us to have this notation there and to include the atomic number. So, standard practice, technically either of these is acceptable. To make sure that you're, not missing anything, it's best just to be more thorough and put both in there. So when we do some practice in class, you're going to see it going both ways. If you see an example given and it includes the atomic number, go ahead and include it in yours. If you see it without, don't feel like you have to. Okay, for my purposes. If students are listening from another teacher's class, they may require differently, but I just want to throw that out there. So these are the different ways that we can notate isotopes. And again, the most important thing is that we know the element and we know the mass number so that we can further identify it from there. Okay, so let's do some examples. Here we have lithium, we have potassium. So if I want to write this one in hyphen form, I would write the full element's name of lithium and then dash the mass number, which 3 plus 4 is 7. In nuclear form, I do it the little 7 up here and then the Li for the symbol. And then another example for phosphorus, it would be phosphorus 31 because 15 plus 16 gives me 31. And then the nuclear form would be 31P. And again, for this lithium, we could put a little 3 down here. For this phosphorus, we could put a little 15 down here if we want to be really thorough in our answer. Okay, now another thing about isotope notation I want to make you aware of. This is something that's going to come up way more in our next unit and really in subsequent units after that too. But I want to go ahead and introduce it because I want you to be so familiar with this, okay? And that's that this notation can also include the charge if the atom is not electrically neutral. So electrically neutral means that the atom has no charge to it. So that means that the protons equal the number of electrons, because the number of positive particles has to equal the number of negative particles for the overall charge to be zero, to be neutral. But that's not always the case, because a charged atom, an atom that has a charge, is an ion. And so this is when an atom will gain or lose electrons. That's what's going to change. The number of the number of protons is not going to change, because that would change the identity of the atom. But with an ion, we're talking about the number of electrons changing, and then that's going to give the atom a charge. And this is really, really important. So let's look at an example. Okay, so this is nuclear notation for Cu, which is copper. From the periodic table, we can look up and see that copper has an atomic number of 29. So we know it has 29 protons. This could also put, the 29 right here if we wanted to. Okay, from this notation, we know that this copper atom has a mass number of 64. And remember, mass number represents protons plus neutrons. Okay, so we can do 64 minus 29, and that will give us 35 neutrons. Okay, so we can figure out that from here. Let's see what else we can figure out. Okay, looking at this plus 2 charge, that means it has 2 more protons than it has electrons in order for it to have a plus 2 charge. Typically, this means that copper has lost 2 of its electrons when it's formed some sort of chemical bond, and that's what's left it to be an ion with a plus 2 charge. So it has more than 2 more protons than it does electrons. So if it has, like we said, its atomic number is 29, so it has 29 protons. That means it must have 27 total electrons in order to have this plus 2 charge. Okay, we can do this again. Let's look at chlorine. Okay, so Cl is chlorine on the periodic table. We can look up on the periodic table and see that chlorine has an atomic number of 17, so we know it has 17 protons. According to nuclear notation, this number up here tells me the mass number, which is your protons plus neutrons. So if we want to know just the amount of neutrons this atom of chlorine has, we'll do 35 minus 17, and that gives us 18 neutrons. Now right here we see that this is an ion. It has a charge. It has a -1 charge. That means it has 1 more negative than it does positive particles. So it has 1 more electron than it does protons. And this will be where an atom like chlorine will gain an electron when it's forming a bond in order to become more stable. And so because of this, if chlorine has 17 protons, but it has a -1 charge, that means it must have 18 electrons because it gained an electron to become this ion. Okay, one more. Let's look at helium. Now, looking at this, let's do the same process with the periodic table. If we look helium up on the periodic table, it has an atomic number of 2, which tells us that it has 2 protons. This 4 tells us the mass number. And so I can take 4 minus 2 to determine that this atom of helium will have 2 neutrons. Now notice we don't see a charge written. If we don't see a charge, that we can assume 0, no charge. We can assume it's electrically neutral. So if it's electrically neutral, if there's 2 protons, that must mean that there's 2 electrons to balance out those 2 protons and give us an electric charge that is 0. Okay, so that's the kind of information we can figure out from this kind of notation. And so we're going to practice that for just a minute. We're going to start a little bit easier, and then we'll get a little bit more complex in our practice problems that we do. So when you get a chart like this, you should be able to fill in the blanks. It's kind of like a puzzle, using the periodic table and using what you have provided. So first, when you're looking for the atomic number, where are you going to find that? Well, you're going to find it from the periodic table. If you're looking for the mass number, you need to be able to add the protons and the neutrons, because remember, this is not on the periodic table. We can't look on the periodic table there. If I want to know the number of protons, that's the same as the atomic number. So I just look back to this column. If I want to know the number of neutrons, I've got to subtract. I take the mass number minus the number of protons, and that's going to give me the number of neutrons. And then for the number of electrons, it's going to be the same as the number of protons if it's an electrically neutral atom. If it's an ion, if it has a charge, it's going to be different. And so you're always going to assume that's electrically neutral unless stated otherwise. So I want you to practice filling this in, and we're going to go over it in class. But again, we're going to keep skipping ahead for the sake of the video. Okay, so let's talk about average atomic mass. We've been talking about the mass number, but we need to talk about this, decimal number that's on the periodic table. You're like, what is that? This is the weighted average of all of the different versions of an element, which are called isotopes. And it is measured in AMU, which is an atomic mass unit. And this decimal number is the closest to the most common isotope of the element because it's a weighted average. It's taking into account how common the isotope is. And so that's what we're going to see here. So yes, there are, hydrogens that have a mass number of 2 that have 1 proton and 1 neutron, but most hydrogens are hydrogen 1 that are 1 proton and 0 neutrons. And so that's what we're going to see reflected here in this average atomic mass. But looking at this is how I know what's the most common version of hydrogen, what's the most common isotope based on this weighted average. I can look at the periodic table and discern that. Now, when given the percentage natural abundance of isotopes, you can calculate the average atomic mass. So you don't have to just look it up on the periodic table, you can actually calculate it. Okay, so what I mean by percentage natural abundance of isotopes is I just mean if you know how common each version of these atoms is, then you can calculate the overall weighted average, which is the average atomic mass. So we just need to know how commonly they are occurring, how abundant they are in nature. And that's often given as a percent. Okay, so let's do an example. It sounds more complicated than it is. We're basically just learning how to do a weighted average calculation, which you can use in so many aspects of life. So for example, calculate the average atomic mass for copper if 69.15% of all copper is copper 63 and 30.85% is copper 65. Okay, so we know that the majority of copper in nature is copper 63, so copper with a mass number of 63. But there is this percentage of copper in nature that occurs naturally that is copper 65. So what we just want to do is use these numbers to find that weighted average, that average atomic mass. So the first thing you're always going to do with these is convert your percentages to decimals. And all you're doing is dividing by 100. Because anytime you make a percent, the last thing you do is times by 100. But since we want to get into a decimal, we're going to divide by 100, which really is just moving the decimal twice. So 69.15%, that's the same thing as saying 0.6915 in terms of like how much it actually is. And that's how we're going to use it in the format for a weighted average. And then 30.85%, that's equal to 0.3085 when we're calculating a weighted average. So keep that in mind. Then what we're going to do is this. We're going to take that percentage that's now a decimal of 0.6915 and we're going to times it by the mass number of 63 because that's going to show us how common this part is. And then we're going to add that to the other part of our average. Remember, an average is always a sum. So we're going to do 0.3085 times 65 to represent copper 65. So first, order of operations, always do your parentheses first. So 0.6915 times 63 gives us 43.5645. And then we're going to add that to this, which is 0.3085 times 65 gives us 20.0525. So you're going to do those first, and then you add them, and you get 63.617. And, to kind of round that with significant figures, we're going to get 64 AMU as the atomic mass unit. That would be the average atomic mass, the weighted average. You just calculated that. So you just convert these to decimals, multiply, and then add. That is it. And we will practice doing this, I promise. It's one of those things that looks a lot scarier than it actually is. You do this once or twice in practice, you'll be squared away on it. Okay, so we're going to practice this more in class, but again, we have a little bit more to cover in our notes for the sake of the video, and that's Bohr models, which I first introduced to you in our periodic table discovery station. So just a quick reminder, these are simple diagrams that show the atomic structure of an atom, and these are nice because they kind of give us a two-dimensional visual of the way that an atom is structured. We can see how many protons are in the nucleus and how many neutrons. We can see how many energy levels are in the electron cloud. And we can see how many valence electrons, or in total electrons that an atom has. So there are some really helpful things about it. But the reason it's not a perfect model is because it is two-dimensional. And we know that these electrons aren't traveling in these perfectly fixed orbits and lines in these energy levels, that they're moving much more chaotically with a lot more energy. And that's what we learned from the electron cloud model that came after the Bohr model. But these are still nice to draw from a 2D perspective and just helping us visualize the structure of an atom. So this is something we're going to do in this class. We're going to be drawing these to help learn from them. Okay, so a couple of steps to help you walk through that process and how to do it. First, you need to know how many protons need to go in your nucleus. And you're going to determine the number of protons by the element's atomic number. So you'd look that up on the periodic table. Then we're going to determine the number of neutrons by subtracting from the mass number. So mass number minus atomic number will tell us the number of neutrons. So we're going to need to know the mass number. Then you're going to put those protons and neutrons in your nucleus because that's where they belong. From there, you're going to look up the period number on the periodic table, and that's going to tell you how many energy levels are in the electron cloud for your atom. And you'll draw those around the nucleus. So if we're in period 3, there's going to be 3 energy levels. If we're in period 2, there's going to be 2 energy levels. Then you're going to put the electrons on each level, and you're going to fill from the inside out. Now, to determine how many electrons they're going to be, unless otherwise stated, we're going to assume they're electrically neutral. So the total number of electrons equals the total number of protons. If they don't tell us differently, that's what we're going to assume. And then at the end, once you're filling this in, check that the number of valence electrons is the same as the group number. Now, another point to emphasize is we only put 2 electrons on the first level, and then from there, you're going to fill to 8 for these purposes as of now. This gets more complicated higher up, but I'll never ask you to draw something that's going to be more complicated than these steps. So this is just to kind of simplify it for our purposes now. We'll get more complex later, but this is how we're going to draw a Bohr model to help us understand the structure of these atoms, and particularly the first 20, because after that it gets a little bit more complicated. Okay, so in class, we're going to practice this by drawing a Bohr model for boron, and then we're going to do a little class project that I think is going to really help you understand this. So stay tuned for that, and I hope this will be helpful.